Hi there. Good evening to everyone. First and foremost, thank you very much for attending this introduction to ANSYS Mechanical webinar. My name is Anas. I am from Cybernet Systems Malaysia, Sdn Bhd. So as you all know, today's webinar is going to be about the ANSYS Mechanical, one of the flagship products offered by ANSYS. So the agenda for today is going to be, first of all, the introduction of Cybernet Systems, and then to be introduction of ANSYS, and then of course the introduction of ANSYS Mechanical products, some of the features of ANSYS Workbench Mechanical, the simulation types, some simulation example, and also some additional options included with the ANSYS Mechanical. And then we go to the coupling analysis with ANSYS, and then I will tell you a little bit information about our service here in Cybernet Systems. And then, of course, we are going to go with the demonstrations and also we wrap with the Q&A session. So now let me tell you a little bit about our company's background. Established in 1985, Cybernet Systems has been providing CAE solution and IT solution through product sales, contract analysis, consulting, and software development for over 30 years now. We have developed a partnership with more than 20 companies, mainly in the United States, including ANSYS, Synopsys, and Symantec. Our head office is in Tokyo. Our development subsidiary consists of Sigmatrix, which is based in USA. And then we have MapleSoft in Canada and also Noisy Solutions from Belgium. The sales subsidiaries of Cybernet System consist of Cybernet China, Cybernet Taiwan, Cyfem, which is based in Korea, and of course Cybernet Systems Malaysia. Cybernet is working with overseas group companies to develop software that will please customers, not only in Japan, but also around the world, and also to develop our group products and solutions overseas. As you can see here, the blue-colored one are our development subsidiary, while the rest is our sales subsidiary. Cybernet Systems Malaysia was established in November 2018 as the fourth subsidiary in Asia. Cybernet Systems Malaysia, our office is based is in KL Eco City, which is located in Bangsa, and has been around for more than 1 year now. Here in Malaysia, we have 6 employees, including administrations, sales, and also technical staff. Our business here mainly revolves around providing CAE solutions, Internet of Things, big data solutions, and also professional services. Our partners up until this point in time include ANSYS, Synopsys, and many others. Now, as you all know, at this point, Cybernet Systems provide all sorts of solutions. Those solutions are, the first one is the CAE solution, or the computer-aided engineering solutions. And then we have some visualization solution via AR and VR. We also have big data solutions, Internet of Things, digital twin, and AI service, some IT solution, and also engineering service. The CAE solutions, which give total support of CAE utilization in various fields. The main application areas include the mechanical systems, fluid system, control system, optical system, and also electrical system. And then, like I said before, we have many other solutions that we provide here in Cybernet System. So next, the introduction of ANSYS. Founded by John Swanson in 1970, ANSYS Corporation is a global public company based in Canonsburg, Pennsylvania. It develops and markets multi-physics engineering simulation software for product design, testing and operations, so on and so forth. As you can see here on the slide, those multi-physics include almost every conceivable physics analysis you can think of, ranging from simple structural analysis all the way to the system simulations. For 50 years now, ANSYS has been the class-leading multiphysics simulation provider. Due to that very fact, ANSYS now has been used worldwide with over 45,000 global customers. ANSYS is also used in a wide range of industries, including automotive industries, electric and electronics, aerospace, and many, many more. So this is basically the summary of what I said on the previous slide. But what I want to highlight here is the ANSYS missions. ANSYS for pervasive simulation. Now, what does it mean by pervasive simulation? Pervasive simulation is an integration across all physics on a single open platform, and the injection of simulation into partners' ecosystems, subsequently helping customers develop innovative products by expanding the use of simulation. It means the use of ANSYS as a versatile tool to be used throughout the design, analysis, production, and maintenance process. You can think of it like this: when the next generation simulation is used pervasively throughout the product design cycle, it will allow designers to see what is too small or too quick to be observed. It will give the development team the luxury to fail before the failure has any consequences, and also to build only the optimal design alternative. Here on this slide are the range of products provided by ANSYS. Now, as I said before, ANSYS provide multiple physics simulation for every type of need. The first one, we have the mechanical solution. We also have the thermal fluid solution, electronic solution, design solutions for designers, and also we have some additional options on top of that. So now the mechanical solution is the one that we will be focusing on today. The analysis included under the mechanical solutions are static structural analysis, dynamic analysis, impact analysis, heat transfer or thermal analysis, fatigue analysis, topology optimization, so on and so forth. Now, of course, ANSYS provide solutions such as thermal fluid solutions, which include the general purpose thermal fluids analysis like rotating mechanical fluids, so on and so forth. So for the design solution, mainly focused for designers and CAD users. Now design solution, this is done by using the ANSYS product called the Discovery Live. You might have heard of it before. And then of course, some additional options offer such as parallel computing module, material selection library, so on and so forth. So let's get into more details on mechanical solution. So basically, there are three types of license of ANSYS Mechanical. In simple terms, the license for solutions are depending on the complexity of a certain need for analysis and simulation. Basically, the highest tier license provides the most access to different types of analysis and simulations and capabilities, while the entry-level license gives you enough access to general purpose analysis. So first tier, the first license is called ANSYS Mechanical Pro. It gives you the access to the solution for linear structural analysis, so model analysis, and also thermal analysis. There are also many more analysis that you can do from using the ANSYS Mechanical Pro. Next, we have the Mechanical Premium. It supports nonlinear structural analysis this time, and also some comprehensive linear dynamic analysis. And then next we move to the top of the range license, which is the Mechanical Enterprise. It combines the advanced functions such as advanced nonlinear materials, transient structural analysis, impact analysis, and also some very highly sophisticated and complex coupled analysis. If you want to know more details about which features included in which license, you can go to the ANSYS website and find out that. Now, if you see on the right side of the screen here, there are some additional ANSYS products that was not included directly into the mechanical solution that we just talked before. Think of it like additional solution for a certain specific problem or certain specific need. The first one here, we have ANSYS LS-DYNA, one of the explicit dynamic solution that ANSYS provide. LS-DYNA is one of the class-leading explicit dynamic solution. It is great for some drop tests or some collision analysis. And then we have ANSYS Autodyne. Like LS-DYNA, Autodyne also provide explicit dynamic solution. It is mainly used for advanced explosion and also impact analysis. And then we have the ANSYS ENCODE Design Live. This is for advanced fatigue analysis. For those who want to take a step further in your fatigue simulation, you can go with this ANSYS ENCODE. It is include vibration fatigue, high temperature fatigue, spot fatigue, so on and so forth. So what makes ANSYS the best multi-physics simulation software compared to the other? Now, one of the main reasons is the ease of use. The ease of use can be achieved thanks to the introduction of ANSYS Workbench. Now, you might ask, what is ANSYS Workbench? It is basically an integrated operating environment that you can connect all process from all analysis environment into one. The Workbench is basically where you lay down all of your work that can be included. That include all type of physics simulation you can choose. For example, take a look at this slide right here. We have the thermal electric simulation, and then couple it with the structural mechanics analysis, and then with the inclusion of the design optimization right here. So basically, there's a 3 different simulation going on here. But with ANSYS Workbench, all of these analysis can be placed in a single platform where you can navigate easily. Now, that is one of the advantages of using ANSYS. I will, of course, explain more about the ANSYS Workbench later on. So now let's talk more about the ANSYS Workbench and how does it work. Like I said previously, ANSYS Workbench is where you can manage all of your analysis or simulation process within one place. It gives us the advantage to easily build our analysis workflow. You can simply just drag whatever system, whatever physics simulation you choose from the left side of the GUI. It is called the analysis system, and then drop it into this white region here. It is called project schematic. And also, it gave us the advantage to easily understand analysis process when everything is laid out according to the workflow. Based on the slide here, we can see the data correlation between the geometry, steady state thermal analysis, and also the static structural analysis. Every individual physics analysis has its own workflow. Now, the workflow is start from the top, which is the engineering data, and then going downward all the way to the results. The status of each cell can be defined by this icon right here. The green check mark basically means that it is up to date. Blue question marks mean the cell is undefined, and then yellow, the lightning icon means the update is required for the particular cell. Okay, now let's start with the feature of ANSYS Workbench Mechanical. I'm going to explain sort of step-by-step analysis procedures when you are using ANSYS. The first one is the material model definition. It means what kind of material do we want to apply to our model. This can be done using the engineering data. The engineering data is basically a material data platform, where we can define the material that we want to use. Here in the engineering data section, you can add your own material with whatever material properties you want to add, as long as you have the required data, of course. Now, if you see on the slide here, there are many settings and toolbox you can go through to fulfill your needs. It is also equipped with a curve fitting function, which can be used, say, for defining hyperelastic or viscoelastic material model, for example. And finally, if you don't want to define the material manually, or there is no need to use a specific type of material for your model, there are tons of materials you can choose from the library available in the engineering data. Essentially, the engineering data provides you with the ability to define your material and also let you choose from tons of available material you can use straight out of reports. Okay. Next, we have now, after we've done defining our material, we must import the geometry data into the analysis environment. For the next step, we are going to import our CAD model into ANSYS. Now, ANSYS do supports many CAD data formats. So most of the time, you don't need to worry about that. One of the advantages of ANSYS is the bidirectional CAD associativity. What this means is with geometry integration solution from ANSYS, you can use your existing native CAD geometry directly without translation into IGES or STEP or other intermediate geometry format. It also provides geometry update based on the parameter setting. ANSYS also provides us with the automatic generation of contact elements at the interface when reading the assembly model. After the CAD data has been imported into ANSYS, the algorithm will read, detect, and generate automatically any relevant contact at the interference of your assembly model. Of course, there is a way to manage the contact manually if the auto-generated contact does not meet your need. So here are some of the examples of the major CAD software that supports bidirectional associativity. You might be familiar with some of the major CAD software, such as CATIA, Autodesk Inventor, so on and so forth. With ANSYS, you will have no problem using the CAD data from that CAD software. Now, of course, general files such as IGS and STEP can also be imported directly to ANSYS as well. Now, let's take a look at mesh generation. In ANSYS, you can be really specific in setting up your meshing, depending on what type of analysis that you are trying to do. If you are not familiar with the world of mesh, ANSYS can automatically generate a good enough mesh for you. Your meshing can also be done according to the way you shape your model. Now, as you can see on the slide here, different types of mesh, such as tetra mesh, sweep mesh, and inflation mesh, can be applied to different parts of your assembly. This is possible due to the fact that ANSYS provides various meshing methods, such as sweep, inflation, hex dominance, so on and so forth. Now, of course, typical mesh controls, such as the element size, can also be easily controlled either globally or locally. Say if you are dealing with the geometry that has a feature that you think not so important for your analysis, instead of going back to your CAD software and modify your geometry, which can take some time, you can use some of the settings inside ANSYS itself. Now, this setting can be called such as model simplification, which include the virtual topology and also pinch. It also have the compatibility with complex shapes using the feature called patch independent. And also ANSYS also have the adaptive meshing, which is automatically generation of mesh that can satisfy analysis accuracy. So the next step for analysis usually will be the definition of boundary condition. So this is basically where you place your loading on your model and then define a fixed point and so on. Based on what you're seeing on your screen right now, the loads can be defined either as constant or a value, or if you want, as a function of time or position. So you can be really specific about defining your loading condition based on your load. ANSYS also has the advantage of flexible selection operation. This supports or the supports of boundary condition Selection can be specified based on the coordinate range, area, volume values, and also the elements of your model. Data mapping function is also one of the neat tricks to have in ANSYS. Say you have an external data regarding the temperature of the model in Excel format, you can import those data directly to ANSYS and then map it on your model and use it as boundary condition. This way, you don't have to reapply the data inside ANSYS manually, then subsequently save a lot of time. So, last but not least, let's take a look at the post-processing of our analysis. For me, this is the most important part in any type of analysis. This is where you finally get your answers to all your hard work. This is where the results or whatever it is that you wanted to study be displayed. In ANSYS, there are so many ways that you can find and display your result. You can just display as a contour diagram or such a vector illustration, for example, and also as a deformation of your model. You can select sectional view and much more. Plus, the great thing about ANSYS post-processing is that you can animate the deformation of your model and see the contour, either it's a deformation contour or stress contour took place. It is a very intuitive way to really understand your analysis. Now, if that's not enough, you want to be more specific, or if you want to see the result at a certain point of time, you can check the tables or graph output that has been generated as well. You can also make your own graph with whatever variables you want it to include. So say if you fancy to extract the result from your analysis and then maybe you want to share your result with, say, your colleague. Now, instead of sharing the whole of your analysis files, which depending on the complexity of the analysis can be quite a big files, you can simply export your result and data to another file format. Now, ANSYS allows us to export it to a text file as an STL output so that you can view and edit it in form shape with the CAD software or with ANSYS Result Viewer. This way, you can easily share your results and data to anyone without having to deal with a very large file. Finally, there is a report function included in ANSYS. What it does is basically that ANSYS will read your whole analysis and then extracting every bit of important information such as material used, material properties, meshing properties, number of elements and knots, boundary condition results, so on and so forth. And finally, compile all of that data and then summarize all of those data into a report. All of these features are really convenient when you have to share your analysis with someone else. See if the previews of the features I mentioned just now on the current slide. So basically, that is the end of the features of ANSYS Workbench Mechanical. Now let's see some of the types of simulation with this ANSYS Mechanical product. Now, if you remember the different license of ANSYS Mechanical, there's a Pro, Premium, and Enterprise, I said earlier. The next part will be some of the simulation you can do depending on what type of license do you have. There will be an icon on every example stated in the particular example. So let's dive right in. Now, as you can see, we have a basic linear structural analysis and also a non-linear structural analysis. Both of these simulation can be done with Mechanical Pro license with some additional feature required, a higher Premium and Enterprise license. The first one is the linear structural analysis. This is basically the analysis for stress, displacement, safety factor, where a certain amount of load is applied, so on and so forth. It is one of the most simplest analysis you can do on ANSYS Mechanical, but still a lot of application can use this type of simulation. And then we have the nonlinear structural analysis. Now, this analysis takes into account the nonlinearity of the problem. Analysis like this has nonlinearity such as geometric nonlinearity, for example, a large deformation, and nonlinear contact can also be done in mechanical. So next we have buckling analysis. Like the structural analysis, we can do both linear and non-linear buckling here on ANSYS. And in engineering, buckling is basically means the sudden change in compression or the wrinkling of the under shear. We have the linear buckling. For linear buckling, only small deformation with no excesses and sudden contact can be considered as linear buckling. And then we have non-linear buckling analysis. This is when you consider the non-linearity that I mentioned in the previous slide. It is a good practice actually to always consider non-linearity when you're not really sure if the problem is linear or not. Okay, so next we have the model analysis. It is available with the Mechanical Pro. So model analysis is to determine the natural frequency and motion of your model or structure. Usually to do this type of analysis, you have to start with structural analysis to create a pre-stress condition. So the example as you can see right here is the model analysis of a flywheel. And then we have a harmonic response analysis. This analysis is to determine the steady-state vibration response of a model or a structure to a harmonic load. Essentially, this simulation is to study the vibration of a structure when harmonic excitation is subjected to it. You can see based on this example, you can observe the deflection versus frequency graph to really understand the vibration. Next, we have the random vibration analysis. This is an analysis for structural response to random vibration loads. In this case, when the input is non-deterministic, this analysis can be very useful. So the input of random vibration analysis is PST or power spectral density. Loads such as acceleration due to the road roughness are most of the time not deterministic. So the time history of the load does not repeat every time the car runs over the same section of the road. It is not practical to define a definite time history of the load. And therefore, random vibration analysis can be really useful in that type of cases. Next, we have the response spectrum analysis. This is an analysis for structural response to a transient excitation condition containing many frequencies and components, such as earthquake and waves. The response spectrum analysis is almost similar to a random vibration analysis, but its input is defined instead of being random. And then next, we have the complex eigenvalue analysis. It is the model analysis considering the inclusion of damping in self-excited vibrations. The complex eigenvalue analysis is used in order to discover the instability represented between two unstable modes at a different frequency. And then we have a rotodynamics analysis. This analysis was usually done to predict a potential hazard of a rotating body due to the rotational speed. It is commonly used to analyze the behavior of structure ranging from jet engines, steam turbines to auto engines, and even a computer disk storage. Now we have covered linear dynamics analysis. Now let's take a look at some of the non-linear dynamic analysis. The first one we have here is the time history response analysis. This dynamic analysis considering the non-linear behavior of the model and also any non-linear problem such as a drop collision. And then of course we have motion analysis. So this is the analysis for obtaining the motion characteristic of our assembly model. This is using the ANSYS rigid body dynamics capability. Essentially, this is how you do the kinematic analysis in ANSYS by using the rigid body dynamic analysis capability. So continuing on the theme of dynamic analysis, we have the explicit dynamics analysis. So the first one is the ANSYS LS-DYNA. LS-DYNA is actually a solver developed by the LSTC, but it is integrated within ANSYS GUI. This way, you can have the ease of use of the ANSYS environment while having the LS-DYNA solving capability. LS-DYNA, like I said before, is a class-leading solver for explicit dynamic analysis. Example of the explicit dynamic analysis is a drop test of a smartphone, as you can see right here on the slide. The next we have ANSYS AutoDyn. Now, AutoDyn is an explicit solver specializing in high speed and even ultra high speed strain rate problems. AutoDyn usually used in military for multiple applications. Some of those applications are high speed ballistic and even explosion. And then we have ANSYS own explicit dynamics. ANSYS explicit dynamics is the solver use is based on AutoDyn. Therefore, the math behind the solver for ANSYS explicit dynamics and the AutoDyn is practically the same. Additionally, while the LS-DYNA and AutoDyn need an additional license for ANSYS explicit dynamics is included with the mechanical enterprise license. So let's move to thermal analysis. We have the steady state thermal analysis. This is an analysis to find steady state temperature distribution and heat flux. And then we have transient thermal analysis. This is pretty explanatory, self-explanatory. This is the analysis where the temperature change with time. And then we have fatigue analysis. Now, this analysis evaluates life, damage, and safety factor using relationship between stress or strain and life of your model. It includes multiple ways of approaching the fatigue problem, such as high cycle fatigue, low cycle fatigue, vibration fatigue, welding fatigue, if you are into the spot, want to know the spot or seam welding life. Then we have a high temperature fatigue and also fracture mechanics. Mind you that some of the fatigue analysis does need an additional product, which is the ENCODE design life. And then we have acoustic analysis. Now, this type of analysis is used to investigate sound wave propagation in closed or open spaces. As I mentioned before, ANSYS have a coupling capability. So the first one I want to show you is the thermal structural analysis. Thermal stress analysis is done by applying temperature distribution obtained by the heat transfer or thermal analysis as a load condition, and then apply it into the structural analysis. This essentially means that the temperature from the thermal load was obtained from the thermal analysis and then applied to the structural analysis as a load condition. So next, we have the acoustic structural analysis. It combines the acoustic analysis and also structural analysis. Next, we have a current thermal analysis. This is an analysis that simultaneously calculates heat generation by the current flowing in the conductor and the resulting heat conduction in that conductor. This basically means that the thermal property of the model is analyzed by taking the current flow from the analysis as load condition. And then we have things like piezoelectric analysis. This is basically an analysis for modeling the piezoelectric body and obtaining the deformation state and vibration characteristic due to the voltage difference generated at the electrodes. And then we have the optimization capabilities of ANSYS. The first, ANSYS use Design Explorer as the optimization. The first capabilities that you can use from the Design Explorer is parameter correlation analysis. It's analyzed the effect of parameters on the results and obtain the correlation and sensitivity result. Then we have optimization analysis, basically the analysis that propose optimal parameter candidates according to goals and constraints. And then we have something like Six Sigma analysis. This analysis to investigate the effect of input parameter variation on the results. Next, still in the realm of optimization, we have topology optimization analysis. This analysis use the phase of a structure as a design variable and then set the goals such as weight and compliance and derives an optimal solution based on the constraint. Okay, so we move to the introduction of ANSYS workbench mechanical products. This is like some of the more examples based on the real life application. I'm just going through this a little bit faster because it is basically the same as before. So here we have the structural analysis of the LCD touch panel. As you can see right here, this analysis example that evaluates the stress generated when the LCD panel is touched. This touch panel using a viscoelastic material, so to take into account the effect of viscosity in the LCD crystal. The finger part is actually a rigid body that expresses the movement of the hand by using joint connection. This way we have more accurate result because we mix the example as close as the real life as possible. So now we have the, this is a structural nonlinearity analysis of a pipe bending process. This analysis is basically pretty straightforward in terms of the objective. You would like to know the behavior of the pipe with a certain material. Its deformation, stress developed, so on and so forth, when undergoing a bending process. So next we have a large deformation analysis of a rubber material. Now this includes the ANSYS remeshing technology. Some analysis, when a very large deformation took place, a convergence can be really difficult to achieve. This is due to the abrupt and significant distortion of the elements of the model. Now, because of that, ANSYS introduced a remeshing technology, which basically means a process of remeshing the model from time to time during the solving process, depending on the amount of distortion happens on the element. So next we have a crack growth analysis based on fracture analysis. The crack growth is one of the failure analysis in ANSYS. So basically this analysis is to evaluate the crack propagation crack propagation direction and distance when material break. So ANSYS Mechanical offers a broad range of fracture mechanics tools, including the capability to calculate traditional fracture mechanics quantities such as stress intensity factor, J integral, and energy release rates, so on and so forth. So next we have the combination of structural and vibrational analysis, which is the stress model analysis. In this analysis, we also include composite material for the turbine blade. As you all know, composite material is not like any type of conventional material. As composite material usually involves with layers and layers of material and having a different type of composite combination. In this case, the composite material was done with ANSYS Composite Pros, ANSYS own dedicated software for composite material, which is greatly reducing the number of modeling. So structural analysis was done to identify the directional vector and of course the stress contour of the turbine blade. And then the model analysis, on the other hand, was done to find the mode shape of the And then we have the PCB drop test. This is one of the explicit analysis. This example of an analysis in which the PCB composed of an assembly model of electronic component was dropped and collided on a rigid concrete floor. Explicit dynamics analysis allow us to capture the very short moment before, during, and after the impact. Conditions are defined for the PCB substrate and the capacitor to separate when a certain force is applied to it. So then again, another explicit dynamic, we have crush analysis of a hollow material. This is an example of analysis in which hollow material is crushed on the axial direction. Implicit solution will be difficult to obtain a convergence due to the high nonlinearity of the analysis. So therefore, explicit dynamic provides an easier way to find convergence when you deal with very highly nonlinear problems such as this. So some additional products for the ANSYS. The first one, we have the ANSYS Space Claim. ANSYS Space Claim is basically a 3D direct modeler with an intuitive operating capabilities. This CAD also have the advantage of two-way linkage via Workbench. What it means, basically, the interaction between setting up your CAD and your analysis in Workbench will be seamless. Space Claim also have an enhanced model correction and simplification function. And then next, we have Granta, ANSYS Granta Selector. This is basically mean you have the capability of selecting your materials depending of various kind of need that you are thinking. You can do that using Granta Selector. And then we have the Granta Materials Data for Simulation. This basically mean a pool or a library of data that you can choose from when you are trying to select any type of materials for your analysis. In this Granta Material Data for Simulation, you have more than 600 materials available to be used directly into your ANSYS. And then some more additional tools, we have the multiscale.sim. Similar to the ANSYS composite purpose, multiscale.sim is an analysis tool that enables the detailed simulation considering the characteristic of composite materials. Now, the main function of these tools are, the first one is the micro model creation. You can create microstructure using multiscale. And then you have the capability to calculate the physical properties such as elastic modulus by using numerical material testing. Now, this analysis is called homogenization. You have the homogenization capabilities in multiscale. Next one, you have tools to analyze and verify by applying the physical properties values to a macro, much more larger model. This is done after you've done the homogenization analysis. You get the data from the homogenization analysis and then use that data on your macro model. And then you also have the tool to extract part of the macro model and study the local behavior in terms of the microstructure. On the slide here, you can see there are many material properties compatible for the homogenization. So next, a quick introduction to our service here in Cybernet Systems Malaysia. We provide support for CAE deployment, including implementation, planning, education, consultation on policies, automation, and so on. So basically, this process includes two steps of service, starting with the startup support service, where consulting and milestone creation are done, followed by construction of simulation environments, so on and so forth. Next step is the operation support service, which comprise of different kind of support during operation, such as daily support service, consulting, sample data creation, automation, customization, so on and so forth. Here in Cybernet System, we can help you by providing various kind of supports on multiple stage of simulation. So that is all for the slide presentation. Now we have been going through a lot of different type of element and different aspect of ANSYS Workbench and Mechanical. So let's dive into a demonstration to give you a clearer view of what you can expect when you are using the ANSYS Workbench Mechanical. So this is some of the example that I'm going to use. The first one is going to be a linear structural analysis of a pipe clamp analysis. This assembly model consists of pipes, clamps, and bolts. We are going to evaluate the internal pressure while the pipe is bolted, and then study static structure analysis of this particular assembly. So for the next two examples, I'm not going through the step-by-step procedures, because the procedures is basically the same as the example one, but I'm going to show you like how we get up to the point, up to the results. How do we get the results? And then next one, we have the thermal stress analysis, featuring the ball grid array, or BGA for short. This particular model is actually a quarter symmetrical model. It is basically symmetrical in this plane and also this plane. We're doing this analysis to evaluate the temperature distribution and thermal stress of the assembly. And then we are also going to take a look into the model analysis. This analysis features the frames construction analysis. We have two different models for this type of analysis, and then we're going to compare the model analysis the more steps difference between these two geometry. So let's dive into the demonstration. First, I'm going to launch our workbench right here. So as you can see, the workbench has already been launched. Now for the first step, because we're doing the static structural analysis, so the first step naturally will be choosing this static structural analysis from this toolbox, then drop it into the project schematic. So as you can see right here, we already load our static structural analysis in this project schematic. Now, if you remember the step-by-step procedure, we are going to start with checking our material that we are going to use. So the first one, as you can see, we are going into the engineering data. Here you can see we have structural steel set as default, and then we have all sorts of material properties for the structural steel. Now, if you're thinking of using different type of material, you can go to the engineering data source, and then you can select like tons of material you can choose from. For example, if you are interested in using aluminum alloy instead, you can choose from the library. So in this case, I'm just going to use the structural steel for the analysis. And then when we finish defining our material that we are going to use, we're going to import our CAD data. How we are going to do that is simply right-click on the geometry right here, then go to import geometry and then browse for our CAD data. So here I have already made a pipe clamp assembly. You see the green check mark here simply means that we are already successfully import the CAD data into the ANSYS Workbench environment. Then next, we are going to start our analysis by going to this model right here, model cell right here. Just double click on it, and then it will launch the ANSYS Mechanical. As you can see right here, it says starting mechanical. That means we are launching the ANSYS Mechanical. Okay, this is going to take a few seconds. Okay, now as you can see, our model has successfully been imported into our ANSYS Mechanical environment. Now, as you can see on the left side here is our project tree. It consists of several setup that you need to pay attention to in order to get final result. Now, first step is going to, we are going to check our geometry. So we have our pipe, and then we have our clamp, and then we have our bolt. Now, if you want to specify the material for your components, you can do by going to this material assignment right here, and then go to this drop down button right here, and then select the material that you choose. In this case, I didn't choose any type of material other than structural steel. So there's only one selection here. And then when we have done checking our geometry, we go to the next important step, which is checking our connection. Now, connection simply means the interaction between components in our assembly. Now, here we have two types of contacts. We have the contacts between the pipe and the clamp, and then we have the contact between the clamps and also the bolts. After we've done checking that, we go to our mesh. Now, say if you not really know how to mesh your model, and you want to see like the general, like how the mesh can be done as simple as possible, you can simply just right click on mesh and then click generate mesh. Here, ANSYS will automatically mesh it for you. Now, of course, you can control the mesh detail using this tab right here. You have all sorts of meshing control. For example, the global element size, you can control right here. For example, I'm going to insert, let's say, 2 millimeter of mesh size or element size. There you have it. That is a little bit finer meshing right there. You can also include a local sizing mesh control. Here for the geometry selection, you can choose whatever geometry that you want to control the mesh, and then simply insert a new element size for that particular components. Okay, so now is for our boundary condition and also loads. The first one on the analysis, I think I want to insert the number of steps by 2. Now, why are we doing that? Because I'm going to include a bolt pretension on our bolt right here. Now, bolt pretension simply means that we include the stress generated in our assembly when we tighten the bolt. So therefore, I'm going to make it 2 steps. The first step is going to be the stress when we tighten the bolt. And then for the second step is the stress coming from the pressure inside the pipe. So how are we going to do that? Is simply right click on static structural here, and then insert the first one is pressure. So we're going to select the surface right here and then select this face here. And then for the magnitude, I'm going to change into tabular so that I can control it right here. Now the pressure coming at the second step. So therefore I'm putting the pressure on the second step right here as 1 megapascal. And then I'm going to insert some bolt pretension to our bolt. Say for example here, I'm going to select this bolt right here, select apply. And then as you can see right here for the first step and second step, the first step is going to be load active. Therefore, this means we are tightening the bolt with 400 Newton of force. And then for the second step, we're going to lock that action into place, like so. And then, of course, we're going to include some fixed support to our assembly right here, because this is a static analysis, and therefore we don't want any rigid body motion. So I'm going to fix this hole right here, simply so. I'm using right-click, insert fixed support selection right here to apply the fixed support. And then as for results, I would want to see the deformation and then the equivalent stress. And then I also interested in the equivalent stress on our clamp parts only. So I can do that. I can specify which components I want to see or I want to study by doing so. Therefore, I'm just going to click solve right here. And then it's, depending on the complexity of your model, the time will depend on that. I believe this is not going to take too long because our geometry is fairly simple. Okay, so our calculation is done. Then we can start reviewing our result. Say the first one here is the total deformation of our assembly. Now you might think that this region right here shouldn't be deformed that much. It is true because this is actually an exaggeration, display. You can control it by here. Say, for example, we want to see the true scale of the deformation. You can see there's barely any deformation because the maximum deformation we have here is 0.028, which is really, really small. And then you can say, okay, this feature right here is basically just to help you to understand the result even more easy. You can also animate the deformation like so. This helps you in understanding what's really going on with the model even better. So you can understand the result even better. Then, of course, we have the equivalent stress right here. As you can see, more stress coming from this part of our assembly for the clamp part. And then, of course, because this is a two-step load, the first step coming from the load from the bolts, and then the second step is the pressure inside the pipe. You can see the stress coming from this bolt first, and then it is pushed slightly upward. I don't know if you can see that. So that basically means the pressure coming on the second step. And then say you want to study just the clamp. What is happening to the clamp? You can, like I do it before, you can specify the components. Now we have just only our clamps. And then the stress contour right here. You can see again the maximum stress coming from this part of our clamp. So that's basically it for the static structural analysis. It is a fairly simple example to highlight just how to do the analysis step by step. And then for the second example, we move to the thermal structural analysis or thermal stress analysis. I'm going to go through this a bit quicker because we're already almost late. Okay, so the first one, we have a steady state thermal analysis on the left side and then static structural analysis on the right side. As you can see, the linkage up here in the middle basically means that these two analyses is coupled together. So if we open it right now, okay. Okay, here we have, like I mentioned before, the ball grid array. This first setup is basically the same as we do on the previous example. The only things different is that the material that I use is different. I assign a specific material for specific components. but the rest of the procedure is basically the same. What is different is because this is the steady state thermal analysis, the input of the boundary condition and also load is going to be a bit different. In this case, I insert the internal heat generation on the chips. Right here, we have the chips inside our assembly right here. And then we have a heat flux on this direction. And then also we have a convection on this surface right here. And then from that, we can get the temperature distribution of our assembly. As you can see, maximum temperature coming from the heat source of our assembly. And then as it moves further away from that heat source, it's getting more and more cooler. And then, of course, we want to study the stress of our assembly. We do so by couple the static structural analysis into our thermal analysis. When we do so, we have these two different analyses in a single project tree. Okay, for the structural analysis, we need to input a typical boundary condition to make sure that our model doesn't move about, doesn't have a rigid body motion. So I put a frictionless support in this surface, and then this surface, and also I constrain this point right here to be as a fixed support. And then this is where we get the load from the steady state thermal analysis. We have the imported body temperature. After we import the body temperature from the steady state thermal analysis, we can know the stress that is caused by the temperature change. So as you can see from the result right here, this is a deformation. So as you can see, it expands. The maximum expansion or maximum deformation here we have is 0.05, not really that big. Of course, it is the exaggeration of the actual deformation. Also, we have the stress, as you can see right here, most stress coming from this part of our components, and then you can see the effects to our solder ball right here. Then you can see the maximum stress is around 115 megapascal. And then we can also study a specific types of assembly or component. As you can see right here, I select the ball grid, solder ball right here and study the stress on this particular solder ball. So that's basically it for the couple analysis. You can study the temperature distribution from the steady state thermal analysis and then use that data to study the stress of our assembly. Okay, so we move to the final example, which is the model analysis. For model analysis, we have two different types of geometry. And then we want to see what is the mode shapes of the geometry. What is the difference between these two geometry in terms of the mode shape? So I'm going to quickly open this to mechanical right here. Okay, so we have this, our first frame, I call it frame A. And then I believe we have the second frame right there, currently opening. So same thing for the first, for this procedure. First we check our geometry, right, like so, and then specify, in this case, I'm using aluminum alloy for our material. And then for this middle part here, we have a point mass. Now in the actuality, there's a object or there's a components bolted to this part of our frame. But in order to reduce the simulation cost and then makes it more simple in terms of the simulation, I replace that parts with a point mass. Now, if you're using point mass, you can specify the mass of that point mass and then the center of gravity of that point mass to mimic it as close as possible to the actual real life situation. Okay, so same thing, check the connection. Now all of it is bonded together. And then we have the mesh of our frame as so. And then for the model analysis, we are only going to need a fixed support. So I fixed these holes and these holes right here. And then simply right click and solve. And then you get the deformation, or not deformation, the mode shapes of our frame. As you can see, you can specify a different, like, maximum number of modes you want to find here on the analysis setting. In this case, I'm specified to find the maximum number of modes to 6. So we have the first shape of our first mode here. And then again, we can also animate our result to make it easier to understand. And then, of course, we have different types of modes here. As you can see, the first mode is happening at the around 51 Hertz of the frequency. Now, for the second frame right here, what I do is actually I increase the height of this part of the frame right here. Now, this will theoretically increase the stiffness of our assembly and therefore increase the strength or stiffness of our assembly. So as you can see, the mode shapes does behave a bit differently. If you want to compare it with these first mode shapes right here. And then, of course, this happened at 51 Hertz of frequency. And then for our improved material, improved assembly right here, it is at 61 Hertz, which is what we expect. It means that this vibration is going to happen at 61 Hertz, which means our assembly is a bit more stronger than the one than the other assembly.